So in this video, we're going to be looking at the Arrhenius equation and how we can actually calculate a value for the rate constant K, look at how that changes between different conditions in a reaction as well. Now we're also going to look at the logarithmic form and how we can calculate values of activation energy as well as our pre-exponential factor A2. Now starting off, we've come across, of course, reaction rates already, and we've said that as temperature increases, our particles overall, they have more kinetic energy, and what we end up with is more particles having energy above the activation energy itself. Now, of course, this leads to more successful collisions, and so we end up with a rate of reaction that's going to increase itself. Now, as temperature increases, we need to know also that the rate constant K, that's also going to increase as well. Now, the way it increases, you can see over here, I've got it on this graph. On the x-axis, I've got temperature in Kelvin. The rate constant K is over here as well. And we can see the type of increase is going to be an exponential. We can see, of course, we've got an upward sloping curve. So yeah, in terms of the Arrhenius equation, we can actually calculate a value for the rate constant K, and we can do that by relating together the rate constant K with the activation energy, EA, the gas constant R, and then the temperature, which is going to be T, and that's normally going to be in Kelvin. Now, if you were to look at the pre-exponential factor, that's something new that's on here that we've not come across before. The pre-exponential factor A is going to be including things like our frequency of collisions and then the orientation as well. Now, the only thing new in this equation is that activation energy is given to you here, and of course, if we were to look at activation energy in any equation, it's given to you, of course, in joules per mole. If it's ever given to you in kilojoules per mole, just remember times by 1,000 to change it into joules per mole. Now moving on then, if we were to look at an example in terms of calculating a value for our rate constant K, we need to know that when we're dealing with a pre-exponential factor A, if we're dealing with the same reaction but we're just using a catalyst or withdrawing a catalyst, or if we're using a higher temperature versus a lower temperature, our pre-exponential factor A is just going to become constant, and so we end up with a new equation over here. Now one conclusion that we can actually make from this is that the fraction of molecules with energy above the activation energy, we can actually give this by using this expression over here. So if we calculate a value, we've basically worked out our rate constant K, but we've also got our fraction of molecules with energy above the activation energy. Look at this example over here. We're asked to calculate the change in the rate of reaction, which we can do by finding the change in the fraction of molecules with energy above the activation energy, or the change in the rate constant K. And of course, we're dealing with the activation energy here being 60 kilojoules per mole, which that of course needs to be in joules, not kilojoules. And then it's going from 10 degrees Celsius to 15 degrees Celsius. Now, of course, we're dealing with the same reaction, so our pre-exponential factor A is going to be constant, and so what we can actually calculate is a value of K for both these scenarios. So yeah, first of all, at 10 degrees Celsius, what I'm going to say is that my rate constant K, that's going to be equal to the exponent of, and it's going to be minus the activation energy. So I'm going to times that by 1,000 to get into joules, and then it's going to be divided by, of course, our gas constant 8.314 times by our temperature in Kelvin, which is going to be 283. We do that, we put in our calculator, we end up with a value that's 8.42 times by 10 to the power of minus 12. There's our first answer done. Now what about if I were to look at this in terms of 15 degrees Celsius? I do the same thing again, but the only thing that's going to change is of course our temperature in Kelvin, which is going to be in this case 288 Kelvin itself. So yeah, I end up with 288 Kelvin at the bottom there. Of course, I work out an answer and I end up with 1.31 times 10 to the power of minus 11 itself. And there's my rate constant at a higher temperature. Now, of course, what I can actually work out now is how many times increase we've got of our rate constant or our rate of reaction. And so that's going to be, of course, our larger number or our latter number, which is 1.31 times by 10 to the power of minus 11. Divided by, in this case, 8.42, and then times by 10 to the power of minus 12. So of course we put that in our calculator and we end up with a value of 1.56 times. And so we know if we increase the temperature by 5 degrees Celsius in this reaction from 10 to 15 degrees Celsius to be more specific, our rate of reaction, our rate constant K, our fraction of molecules with energy above the activation energy increases by 1.56 times as well. So yeah, I've got a task for you to do. Feel free to pause the video, have a go at the following question, and then resume once you're ready to go over the answer. Just be aware that the only thing changing here is the activation energy itself. So yeah, we're told over here that reaction X can take place with or without a catalyst. The uncatalyzed reaction has an activation energy of 50 kilojoules per mole at 20 degrees Celsius, and the catalyzed one is going to be 25 kilojoules per mole at 20 degrees Celsius. We're asked to calculate how many times more molecules have energy above the activation energy. So again, we're looking at the difference in terms of the rate constant in this case. So yeah, if I were to look at it right, I've got the uncatalyzed reaction to start off with. So of course, I've got the uncatalyzed reaction, and of course, we're going to work out a value for K, and to do that we're going to do the exponent of minus the activation energy, which is 50 times by 1000 divided by our gas constant 8.314 and times by our temperature, which in this case is going to be 293 itself. We do that, we end up with a value of 1.22 times 10 to the power of minus 9. So there's our first answer done. Now what about our catalyzed reaction? Because our uncatalyzed reaction is going to be done. Well, in this case, right, if I were to work out the rate constant K, I'm going to change that 50 to 25. So I end up with 25,000 at the top divided by 8.314 times by 293 itself, because the temperature is the same. So yeah, I do that, I end up with a value of 3.49 times by 10 to the power of minus 5 itself. And of course, there's my answer for that second one. Now, how to go about finding how many times more molecules we have with energy above the activation energy, or in other words, finding, of course, how many times greater our new rate constant is going to be. Well, what I would do is of course, I would take my latter number, my larger number in this case, that's going to be 3.49 times 10 to the power of minus 5, divide that by my smaller, my number before, and that's going to be 1.22 times 10 to the power of minus 9, and then of course I work out an answer in my calculator. That's 28607 times, right? So we know, of course, we end up with 28607 times increase in the rate of reaction, which seems like a massive number compared to the last one, but of course we're looking at a catalyst here, and that's how we can answer that question. Now moving on then, how can we actually work out a value for our activation energy and our pre-exponential factor? Well, this is where we need the logarithmic form of our Arrhenius equation. Now of course you will end up with this on your formula sheet, which of course is going to be this equation over here, but what I prefer to remember is ln K is equal to minus EA over R times by, of course, 1 over T, and then of course we're going to add that ln A on there as well. And what we can see is we've got y equals mx plus c. Now, of course, if I were to look at our normal graph where we've got our rate constant K on the y-axis and then the normal temperature, not 1 over T, but normal temperature on the x-axis, we end up with that exponential graph. But to make it a straight line graph, what we can actually do is we can take our values of temperature, which of course will be given to us in the exam. Same thing with the rate constant as well. And we can do 1 over T and then ln of that K as well, the natural log of K. Now, of course, if I were to show you an example, let's say if I were to do 1 over the temperature of 290, I would end up with a value of, if I put in my calculator, 3.45 times 10 to the power of minus 3, and the units is going to be per Kelvin. So in that case, I would of course plot that in my table over here. So I end up with 3.45 times 10 to the power of minus 3. Now what about my rate constant K in this case, right? How could I actually process that? Well, I've got a value over here of 1.99 times 10 to the power of minus 4. And what I'm going to do is I'm going to work out the natural log of that K value. So in that case, right, I'm going to do ln K. So I'm going to do ln, and it's going to be 1.99 times 10 to the power of minus 4. I'll put that in my calculator. I end up with a value that's going to be minus 8.52. So yeah, I end up with minus 8.52. Now, of course, you can see over here your y-axis is going to be negative, and then your x-axis, that's going to be positive. And of course, you can actually get different graphs with different data. But the sketch I've drawn, so it's easier to see, is going to have positive for both our x and y values. But yeah, you'd normally plot this data in a graph, and then you can actually find your values in terms of y equals mx plus c. Now, in terms of this, right, to find your actual y-intercept, that's going to be easier. You're going to look at where x is going to be equal to 0, which of course you can see is going to be over here, and you're going to extrapolate this line so that you find the y-intercept. So the point at which x is going to be equal to 0, where does your line of best fit touch the y-axis? And you can see it's going to be that point over there. Now, of course, let's say if that value was c, right, our y-intercept was c, we can say that our natural log of a, our pre-exponential factor, which you can see over here is going to be c, is going to be equal to, of course, c over here. How do I get the pre-exponential factor though? What would I do? do? Well, I would take the inverse operation of natural log, and so I would take the exponent of our c value in this case, and that's how you can calculate a value for your pre-exponential factor. Remember that the y-intercept isn't the pre-exponential factor, it's the ln of the pre-exponential factor, so you need to process that a bit more. Now, what about if you were to work out a value for activation energy? How would that be different? Well, of course, if you were to look at the term that involves activation energy, of course, it's going to be m, the gradient, which is going to be minus EA over r. And so if you were to work out a value for the gradient m, right, you can actually rearrange this. So let's say if m is equal to minus the activation energy over the gas constant. To get activation energy on its own, you can either take the negative gradient or the negative gas constant. I prefer just to say negative m. So if your gradient is negative, which it already is, just remember you're going to do minus the negative gradient times by the gas constant, and just remember your answer comes out in joules per mole itself. So yeah, all we're doing is we're plotting our x values, our y values from our Arrhenius equation. We get a graph in terms of y equals mx plus c, and we can find the gradient, do a bit of processing, and then find the y-intercept and do a bit of processing to get our answer. So yeah, I've got an example here. Let's try this one. So we're told a student determines the rate constant k at different temperatures t. The student then plots a graph of ln k against 1 over t as shown. We can see over here, of course, our x-axis is going to be times by 10 to the power of minus 3. Just be aware of that because sometimes it might change. So yeah, if we were to look at this, the first thing is I need my Arrhenius equation in the way I like to remember it, which is ln k is equal to minus EA over r. So there's our m value, and then times by 1 over t, there's our x value, and then of course added to ln a, there's my pre-exponential factor. Now the first thing that I'm going to do is I'm going to extrapolate my graph, because I know my graph starts at 0, 0, although it's not labeled over here. You know x is going to be equal to 0 over here, so I should end up with something that looks like this if I continue the line of best fit with a ruler. Now that's done, I think we can go ahead and answer this question in terms of the activation energy to start us off. So I'm just going to pick any two values that are nice and easy to read, and I'm going to go with this value over here, which is approximately going to be, for my x value anyway, 1 times 10 to the power of minus 3. So I end up with something that looks like this over here, and I'm going to plot a coordinate for that as well, 1 times 10 to the power of minus 3, so I can work out my gradient quite easily, and I can see, of course, my y value is going to be 7.5 itself. I'm going to do the same thing for, let's say, 2 times 10 to the power of minus 3, because that point seems easy to read. That's going to be this point over here, and that's going to be, of course, 2 times 10 to the power of minus 3, and then we're going to end up with a y value being 5.5 itself. Now that I've got that information, of course, I'm going to label it like this. There's point 1, there's point 2, and of course, when we come to working out our gradient, right, once we found nice points that are easy to read, we can, of course, take our change in y over the change in x. So I'm going to do y1 minus y2 divided by, and then it's going to be x1 minus x2. And so if I sub in my numbers, I've technically got over here, it's going to be 5.5 subtracting 7.5 at the top. That's our change in y. And don't forget the powers, because of course, remember what we said over here, it's going to be times 10 to the power of minus 3. I've got 2 times 10 to the power of minus 3, and then we're going to subtract 1 times 10 to the power of minus 3. Now I'll put that in my calculator. I end up with some nice round numbers in this case, because obviously this data is made up, and that's going to be minus 2000 itself. I get 1 mark there so far. Now what about finding activation energy? Well, that's going to be, of course, equal to the negative gradient, so negative, and then it's going to be negative 2000 in brackets, and then times by our gas constant 8.314, and we end up with a value that's going to be 166 and then 28, and it's going to be joules per mole in this case. Now, of course, we need to convert that. So, of course, our activation energy is going to be equal to 166 and then 28 divided by 1000. Now, just remember, normally we are asked to give this to 3 significant figures, and that's going to be 166 in total, kilojoules, and then per mole. Just be aware though, activation energy is always positive because it's the minimum energy required for a reaction to start. So yeah, what about if I'm finding my pre-exponential factor in the next question? Well, of course, I need to look at my y-intercept, which is going to be this point over here. So I'm going to circle that as well. I know my ln a value, because remember, it's not going to be a pre-exponential factor. It's a natural log of it. That's going to be equal to 9.5. And so I know to find a, I'm going to do the exponent of 9.5, and that's going to be equal to 13360 itself. Now in this case, I don't actually know what the units are, so I'm not going to put any units down, but it would be the same as the rate constant. And yeah, you'd get 1 mark here and 1 mark over there as well. Now moving on, feel free to pause the video. I want you to have a go at the following question. Once you're ready to go over the answers, resume, and we'll go over it together. So yeah, if you were to look at the following question over here, again, same type of thing as before. We're going to need our Arrhenius equation where we've got a graph of ln k against 1 over t. So I know ln k, that's going to be equal to minus the activation energy over the gas constant times by 1 over t. And then, of course, I end up with adding ln A itself. Now, in terms of this, I'm going to extend this line of best fit so it touches the y-axis, because, again, I can see x is going to be equal to 0 over here. I can see my y-intercept. So I end up with something that looks like this. So yeah, now I've extended the line of my best fit. I know, of course, I can work out a value for my activation energy quite easily. I'm just going to pick out 2 points. I'm going to go with this one over here, and then I'm going to go with this one over here as well. Just because they're nice and easy to read, they land on the corners of the square. So yeah, I'm not really going to use proper standard form over here, but I've got times 10 to the power of minus 3. So I've got 0.75 times by 10 to the power of minus 3 over here. That's going to be, of course, our x value for that coordinate there. And then I've got 5 over here, which is going to be my y value. I do the same thing on the other side. Of course, I've got 5.75 on that coordinate there, times 10 to the power minus 3. And then don't forget as well that your y-axis, that's going to have a value over here as 1.5. So yeah, of course, I'm going to label these coordinates. We'll go with that one being 1. That's going to be 2. So yeah, I can go ahead and work out a value for my gradient now, and that's going to be equal to, and then it's going to be 1.5 subtracting 5. And that's going to be divided by, in this case, it's going to be 5.75 times 10 to the power of minus 3. And then that's going to be subtracting 0.75 times 10 to the power of minus 3 as well. Now I do that, I end up with a value that's going to be minus 700, and there's my gradient there. Now the next step is I need to work out activation energy, and that's going to be equal to minus the gradient of minus 700. And then that's going to be times by our gas constant, which is going to be 8.314. Now we do that and we end up with a value of 5819.8, and that's going to be joules per mole as well. Now what about if I were to work out our value for my activation energy in kilojoules? I take that 5819.8, divide it by 1,000, and so I end up with a value that is going to be 5.82 in this case, to 3 significant figures, and it's going to be kilojoules per mole in terms of the units as well. And there's our activation energy done. Now what about our pre-exponential factor? Well, we know that our y-intercept, ln A, that's going to be equal to, in this case, 5.5, and so A must be equal to the exponent of 5.5, which is equal to, in this case, 245. So yeah, there's our answer for our pre-exponential factor. 2 marks there as well.